Hi, in this video I'll explain what a simple harmonic motion is, and I'll show you a quick mathematical demonstration of the relationship between this one and the trigonometric functions. First, let me quickly explain what a simple harmonic motion is. And I'll be focusing on the principle of the motion, the principle that governs the motion. So here's a typical example. So here's a mass attached to the spring system, and there's a gravity acting on it, and there's air filled in this space. But right now it's hanging in there, not moving. But if you pull it down and release it, and then you can imagine it's going to make this motion of going up and down. But in this ideal experiment, we will ignore the air for air drag. So I'll write down no air drag is involved in here, but only the spring is, and together with the gravity, is creating the motion that's going up and down. So it's moving up and moving down by the same amount. And this center position is called equilibrium position. So it's equilibrium position. Since this motion is described vertically, I think we'll describe this position as y centimeter, where y is a magnitude, add t seconds, for example. So you can write this position as a function of time as it's released from somewhere. So what makes this harmonic motion is this following principle that governs this motion, which is the following. So this principle is also known as Hooke's law. It's the following. If it is moving like this, and it is the Newton's idea, it's a force is acting on it. That's why it's moving up and down. What changes its speed and direction is exactly that the force is doing it. So it's the relationship between the force and this position, and that's the principle we're talking about. So force is represented by this capital F. So here it is. So right now there's gravity and something is coming from the spring system. When it's not moving, that what spring is pulling and then gravity is pulling down, and they cancel each other and it's not moving. That was the equilibrium position. Now after you stretch it, it's going up and down, and in that case the force is changing. So principle says the following. If, for example, the mass is in this location, since it's actually moving up and down, but there's too much things written on this one vertical line, so I moved it over here. We don't know if it is going up and down at this moment. Maybe it was going up and heading up and it was coming down. But the principle says if you're in this location, the force that is acting on this mass, created by the combination of both the spring system and the gravity, is this direction. Something is, altogether, it is pushing down toward the equilibrium position. That's the direction of the force, and the magnitude of the force is exactly y. No, it's not exactly y. It's directly proportional to y. So k times y. There's this fixed number k, and it's directly proportional to this position. So if it is away from, for example, if it is even further away from this position, force is again acting toward to the equilibrium position, but the magnitude of the force is directly proportional to this position. So if it is further away, displaced from the equilibrium position, the force in here is a lot stronger. For example, if I exaggerate a little bit, a lot stronger than force acting on in here. That's what this says. Qualitatively, that's what it is, but it's more specific. It is, y to the first times a constant. It's a more specific version. So here, statement goes like this. The force acting on the mass is directly proportional to the magnitude of the displacement in here. Like this. And after you write it like this, is something that you have to take care of it here, is this direction of the force. Let me go ahead and write sample some of the positions down there. So if I have a position down here and there's a force acting on that one toward to the equilibrium position, and the magnitude of that force is determined by this formula. Some purport constant times is magnitude of the displacement. Here you can see y is a positive number, and if we set this one, equilibrium position is a y equals 0 number, and here down here y is a negative number. So y itself has a sign built in it, and then we have to use this sign to implement it here and its force part, so that it indicates which direction its force is acting on. So when y is a positive, if you look at it here, the direction of the force is kind of downwards here. So that indicates that the sign of this force must be negative. Right now it has Kn positive, so in this case here it's not matching. So we have to fix our formula like this is equal to the opposite sign. So let's check that if this is still valid for the bottom part here. When y is negative, displacement is below the equilibrium position. The direction of the force toward to the equilibrium position is kind of upward. That's the direction of the force, so that has to be positive together with this negative, and the sign of y being negative here together is a positive. The forces kind of have the right sign. It turns out this is a formula. So the final formula is the magnitude of the force is directly proportional to the displacement with this opposite sign. That seems like the governing principle. If this much of the force is acting on at each position continuously, that probably determines this motion we observe as you stretch and pull down. And it is a standard course called the differential equation. Right there, and differential equation, in that mathematics course you learned on what the formula of y is. In other words, can we describe this position y centimeter as a function of time in terms of some function we know? The answer is, so here's the answer that you learn. Not only you just learn the answer, you learn the mathematical way of understanding why this has to be in this way. So y, it turns out, is a combination. Turns out if some motion is governed by this principle called Hooke's law, I forgot to write that, Hooke's law in here, combinations of sine function, the k is involved in here, I think, kt, and cosine kt. And you can easily check these two functions. Actually, in the first year calculus course, after you learn first one variable calculus course, you can easily check these two functions are the functions that satisfy this principle. But what's interesting in this differential equation course you are going to learn is that, and this is the only function that we have discovered that's not the statement. This is the only function in the whole world, and we can guarantee that, and that must be it. There's no other possibility than sine kt. And you can make such a bold statement in mathematics because it's not physical world. It is something that the way we understand in a mathematical possibility sometimes can be rigorously argued and conclude such a strong statement. In the whole world, in this generation, after more generations, there won't be any other functions. This will be it. And that's an interesting part. And another interesting part is this motion governed by this principle. Then all of a sudden it involves the triangle. And that's another interesting part to me. So next part will be more of a demonstration using the computer animation.